Okay, this video is about the key features of exponential graphs. So we start, the basic function of an exponential graph, or the parent function, is y equals a times b to the x. Now when we have these exponential functions, a and b are always going to be constants, meaning they're numbers. A cannot equal 0, which makes sense because if you multiply 0 times anything, you get 0, and then you wouldn't have a function. B has to be greater than 0. And b also can't equal 1 because 1 to the fourth is 1. 1 to the 10th is 1. Anything to the 1 is 1. So you're not getting anywhere. It's not going to make it an exponential function. Okay, so if we're looking at just the parent function, these basic models. Now normally with all the other graphs we've done, there's just one parent function. Well, this one you can change the base. Like this one's got a 2, this one's got a 3. So there's all these different parent functions, but they all have the same shape. So we're not going to worry about memorizing the numbers too much, but all these parent functions have the same features. The first one is they will all contain the point 0, 1. And the reason for that is if you put 0 into this x, any number, so take it like 7 to the 0, equals 1. Anytime you have any number at all to the 0 power, it equals 1. So in all of these basic parent function graphs, you're going to have the y-intercept of 0, 1. The second thing, it always has an asymptote on the x-axis. Now we talked about asymptotes when we had irrational functions and we had two asymptotes and we had the two different arcs in the opposite corners. Those were rational, but this time it's a different picture, but we are going to have an asymptote on the x-axis. And remember, that means it's going to get really, really close but not actually touch the x-axis. The other thing is if this a out in front is between 0 and 1, so think decimal or fraction, then the graph is going to decrease. That means exponential decay. But if a is greater than 1, that means the graph is going to increase, and you want to think exponential growth. When you do your homework, you're going to need to know the two phrases, exponential growth and exponential decay. So if it's going up and a is greater than 1, it's growth. If a is between 0 and 1, it's going to be decay. Now, because there are so many different parent functions, I can change this number to 2, 3, 4, 5, 6, 7. I keep going and going. I'm not going to have you memorize the numbers. You could easily calculate it. 2 to the 0 is 1. So you could have 0, 1. You could plug in 1. 2 to the first is 2. You can plug in 2. 2 squared is 4. You could keep doing all this and getting the points for sure. But what I'm going to show you is how to put this in a calculator and get these points in your calculator. So if you open up your calculator, and you go to the y equals, then we can type in the equation 2, and then you use this little caret button over here, to the power of x, okay? And then you're going to hit, then we want to go to graph. Now some of you may not have a standard window, so you're going to have to hit zoom 6, and then you've got your standard window. And here is my graph. Now notice as it goes to the right, it shoots up. So this one is going to be exponential growth. Now it looks like it touches the x-axis, but it doesn't. It just gets really, 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 really close. So it's 0.000000000, like 100 zeros and then a 1. So I mean, like crazy close, but doesn't actually touch it. So when we actually get numbers in our calculator, the calculator is going to think it's 0 because it's so close it gets confused, but it doesn't actually touch it. Okay, so how do we get actual points without having to calculate them? Well, right above the graph is a feature called table, and if we hit second and then table, it'll give you some values. So you can scroll up and down here and get all sorts of numbers that you want, plug in whatever you want, or you can get some ones that are definitely more reasonable to graph, which are, definitely not these numbers. Let's go back up here. I scrolled a little too far. All right, so here are the numbers. Oh, now it's going to go on forever and be crazy. Okay, here are the numbers that you want, some in here. All right, I paused the video so I could reset the calculator, but here is where we're looking. So what does this mean? This means that you've got an ordered pair at the point 0, 1. So you're going to go over 0 on the x, up 1 at the y. To plot this one, you're going to go over 1 on the x and 2 on the y. 2, 4, 3, 8. These are all points. Negative 1.5. These are all points on the graph that you're going to plot. So now that we have the points, we can go over to our graph and plot those on the graph. So make this a little bit bigger. So at 0, you always get 1, 1, 2, 2, 4, 3, 8. Now some of these you're just going to memorize because they're not that hard. 4, 16. Obviously that time is not today. Okay? And it's going to get closer and closer to 0. So this is what your graph is going to look like. Okay, so now that we know what the graph is going to look like, we need to find the domain and the range. So the domain goes left to right. Well, I can put in all the negative x's I want and all the positive x's that we want. We saw that when my calculator got out of control and went too far. So the domain is going to be all real numbers. The range, though, we've got to go from the bottom up. Oops, I didn't mean to hit that. So we've got nothing, nothing, nothing. It starts at 0. Now remember, it doesn't actually touch 0. It gets really, really close. So we're just going to put a parentheses, not a bracket, and then it continues on up so it goes to infinity. The y-intercept, that's where it crosses the y-axis, and all these cross at the point 0, 1. Okay, I like to call these parent functions the base model. That's where we're starting at. Okay, so now let's do f of 3x. So we go back to our graph. We're going to clear this out. So we have 3 caret x. And now we can hit the graph button because we already set it to a standard window. So here's the graph. Looks a lot like the other one, crosses at 0, 1, but this one's going to go up faster. Now if we want some of those values, remember we're going to find that in the table. So we have second, table, and now here are the numbers. So at 0, we can plot 1, just like we expected. 1, 3, 2, 9, 327 doesn't fit. So plot what's reasonable and what you can. So let's go over here, graph this. So at 0 is 1, 1 is 3, 3 squared is 9, 3 cubed is 27, which is off the graph, but we've got decimals here. So this is your graph. Okay, the domain, I can put anything in it for x, so my domain is all real numbers. The range goes from the bottom up, so there's nothing down here. It starts at 0, but it doesn't actually touch 0, so there's a parentheses, and continues to climb, so it goes from 0 to infinity. It crosses the y-intercept at 1, so it's 0, 1. Okay, we're going to do this again, but this is now that we've added a negative, it's no longer the base model. And remember what we've learned before, that negative is a reflection and it flips it upside down. So let's see if that really happens. So instead of doing these one by one, we're going to be a little more efficient and put them both in our calculator. So let's go here, clear this out. So the first one I'm going to do is negative 2 to the x. Okay? And the next one I'm going to do is negative 3 to the x. Notice that when I put the negative, I use this button down here by the enter button at the very, very bottom. You cannot use a minus sign. Your calculator will give you an error. Okay, we can look at the graph so we can see what happens if we put in a negative. And we know a negative is a reflection, so instead of going up, it opens down. So that's exactly what we think. So there's the 2x one, and here is the negative 2 or 3x one. Okay, so now let's go to our table. So second table. So the first graph that we put in is 2, so that's in that y column. So when we go to graph the first graph, I'm going to plug the point 0, negative 1, 1, negative 2, 2, negative 4, so forth and so on. When I graph the next one over, I'm going to graph 0, negative 1, 1, negative 3, 2, negative 9, 3, negative 27, and keep going like that. Okay, so let's get those graphs graphed. So negative 2x. Now, instead of starting at 0, 1, it's a reflection, so it opens down. So it's 0, negative 1. And then I've got 1, negative 2, 2, negative 4, 3, negative 8. That'll be enough for right now. Negative 1/2. So this looks like that. It's not perfect. I'm not good at drawing them upside down. Okay, this one at 0, negative 1, 1, negative 3, 2, negative 9, negative 1, negative 1/3. So there is our graph this way. So let's talk domain and range. Well, just like all the other ones, I can put in any number I want for x. So my domain is going to be all real numbers here, and it's also going to be all real numbers here. The range, now remember the range goes from the bottom up, and down here I've got lots of points, and they just keep going and going and going. So it starts way, 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 way down low, it starts at negative infinity and it stops at 0. It doesn't actually touch it, so we're going to have a parentheses. Same thing on this graph over here. Okay? And now for the y-intercept, because this one was a reflection of the base model, then it started, instead of at 0, 1, it starts at 0, negative 1 is the y-intercept, and this one is at 0, negative 1. All right, let's graph these. What happens if the number is a fraction or a decimal? So again, we're going to go back to our calculator. We're going to hit y equals. We're going to clear all these out, and we're going to be efficient about it and do both at the same time. Well, let's first do this. Let's look at one of them. So 0.5 to the x. Make sure you have that 0.5 in there. Let's graph it. So let's see what happens here. Oh, this one starts high and down low. So this is an example of exponential growth. But now, exponential decay, because it goes down really fast. Okay? But if I put a negative in front of it, then it's the reflection. So it should flip it over. Okay, so I have negative 0.5 to the x, and check that out. And let's see, does it flip it over? It most certainly does. Okay, so now we want to get the table of values. So my first graph is in the y1 column, so I'm going to plot the point 0, 0, 1, 1.5, 2, 0.25. Now, these are going to get really small, so it's going to be good to get some negatives in there. Negative 1, blah, blah, blah. So that's what we're going to want to plot here. So on this one, at 0, 1, it was here. Oops, at 0, it's still at 1, but now it gets really, really small. But here, negative 1, 2, negative 2, 4, negative 3, 8. So we've got some decay. Okay, but this one is a reflection, right? So if we went back and looked at the graph, it's a reflection. It's this red one. So it flips it over. So over here at 1, it's getting really close. 0, negative 1, negative 1, 2, negative 2, 4. So the graph looks like this. Now let's compare the domain and range on this. On the left, the domain, I can put in anything I want. So again, I've got all real numbers. The range, there's nothing down below, and it starts at 0, so it goes 0 to infinity. It is a base model or a parent function, so the y-intercept is 0, 1. Over here, the domain, again, you can put in anything. The range starts down low, but way, way down low at negative infinity, and goes all the way to 0. Because it's a reflection, the y-intercept is at 0, 1. Okay, we're going to go to the next two kind of fast because I think you'll pick it up pretty well. So we're comparing two things. We're comparing 2x, or 2 to the x, and 2 to the x plus 3. So let's put this in our calculator. So we're going to clear this out. Okay, so the first one I'm going to do 2 to the x. We know what that graph looks like. We've already done that. And now I'm going to do 2 to the x, but make sure you arrow over because we don't want the plus 3 with the x, and say plus 3. Okay, so the first graph is the original. The second one gets moved 3 units. Well, let's figure out which way it gets moved. So there's the original. And here's the new one. Now pay attention to the y-intercept because that's going to help us figure out. Okay, here's the new one. And if I look, before the y-intercept was at 1, now it's at 4, which is 1, 2, 3 positions higher. So adding that number on the end shifts the graph up. Now I'm not going to plot the points because you can do that on your own. But adding this plus 3, it shifted the graph up 3 units. So then if we subtracted the 3, it's going to shift it down 3 units. Okay, well let's look at this one. We got 2 to the x and 2 to the x plus 2. So let's put it into the calculator. Now, when I enter these things, now when I do 2 to the x, that plus 2 is up there in the exponent. It's not big off to the side, it's up to the exponent. So now let's graph it and see what happens. Okay, so here is my original. Again, now pay attention to where this y-intercept ends up so you can see what happens here. Okay. So it changes by shifting over to the left, okay? Because it was here and it moved over to the left. So when it is up here with the x, it's to the left. And remember, the x, it's always the opposite of what we think. So it's going to shift to the left 2 units. And if it was minus, then it would shift to the right 2 units. And that is it on key features.